think about now. All right. So, is that visible? Yeah, I clearly have like a good side and a bad side. Anyways, so what are we going to talk about today? Any guesses? So we're going to talk about what a derivative is. So what is a derivative? Okay, I have some graph, right? Draw some arrows here. Let's draw an arrow here. I know this is some function f of x. What's the derivative? Yes, what's the derivative? Please. Okay, no, but on this diagram, what should a derivative say at this point be? Yes, the slope of the tangent line. That's a pretty good answer. As good an answer as most of them. Okay, so the slope of the tangent line is f prime of x. Okay, sure, but what does this slope, what does the slope do? Why is it useful? Rate of change, yeah, sure. Why is it useful? What can I use this line for? Exactly. So I can take this, and using the slope, I can approximate this function, right? So I can say that actually f of x around x naught, so let's say f of x plus some delta t should be approximately f at, let's do x naught, f at x naught, yeah, plus f prime at x naught times delta t, right? So this is a kind of linear approximation. Yes? Make sense? Okay. Do you agree? What you can also realize is that actually this is a linear function, right? Multiplying f of x naught by delta t, that's a linear function, right? This is some linear function, df, right? That takes in a vector in R and outputs another vector in R by taking delta t and mapping it to f prime x naught delta t. You agree with this, yes? So the derivative helps us define a linear approximation, where essentially what we're saying is we want to take, well, that's fine. I don't know, the door was in fact locked. I'll unlock it. Okay, so we're just talking about what a derivative is, right? And so we are now realizing that the derivative is actually a kind of linear approximation, where you have some function, and in some kind of small neighborhood around some point x naught, I can approximate it by a kind of shifted linear function, right? So you have like a linear function plus some shifted term. Do you agree? Okay. Yes. Do you agree? That's fine. So let's say this one more time for the people who are a little bit slow with plotting, not with thinking. Is if we have some kind of function, right? What's the derivative? The derivative is the slope of the line. But really, in that case, what I can do is if I look very close to this region around f of x, I blow it up. This function looks almost linear. So the derivative defines some linear function which can be used to approximate this function in this point. Right? So in some sense, the derivative, so this is kind of the big takeaway, is that derivative is a best linear approximation. Approximation at a point. So let's go here at a point. Now, okay, in general today, a lot of the things that I'm going to say are going to be like not really rigorous. I'm going to kind of tell you intuitively how things work and how they should work, and hopefully that will be intuitive for you. And that should be sufficient. So I'll try and prove some things, but if I really try to prove everything I say today, it would be just very, very long. Because like if you open Moncrief and look at some of these proofs, they're like 4 pages long because there's like a lot of details. But the point of why it all works is like those details aren't all entirely relevant. I want you to get a sense of why all this works. Okay, now we're going to consider a slightly different case, slightly more complicated case. Okay, so this is bad because I like took up the whole wrote this in the middle of the board. I should have written it like more to that side. Okay, that's fine. I will just turn this around and write somewhere there. Okay, that's good. So now, okay, now consider the following case. Let's look at a simple case. Suppose I have a function f that's going from Rn into say R. Okay, and I want to define a derivative for this function, some kind of derivative, right? So if I want to define a derivative for this function, what do I want? I want to define some kind of yes, I want to define something that would be a linear approximation at a point. Okay, so that's the idea. This, like you can now think of the derivative as something that linearly approximates my function at a point. Okay, and then we'll realize it also kind of does something else, but that's fine. So let's see. Well, okay. Some of you might already realize what the answer is. We're going to still try and do like a simple thing. We won't define the full linear approximation straight away. So kind of, what do I have? Say, I have some vector space. I have vectors in R2, let's say, right? And then these get mapped to just the real line, right? And this could be a nonlinear function. F could be anything itself. Right? It doesn't need to be a linear function. Yes. Okay. So I suppose I'm like kind of at this point, right? This is my x naught. Suppose x naught gets mapped to some, I don't know, y naught here. And I want to define a linear approximation, right? Okay. So now, what do we already know how to do? Yes. So we already know how to do single variable calculus, right? So let's try and see, okay, can we maybe first do a simpler problem and not do a full linear approximation of the whole thing, but maybe try and do single variable calculus first. What is a thing that we could do here? If I wanted to do a single variable, if I tell you single variable in terms of vector spaces, what should you be thinking about? Exactly, one coordinate. So this means in linear algebra terms, I'm looking at a subspace, and what kind of subspace? Yes, one-dimensional subspace. So yes, but one-dimensional subspace. So let's just choose some vector, some direction. You can choose any direction. You agree? Let's choose, say, this direction. You agree? V. And so what can I do? Now, I can think of x in what way? I can think of f of x. Suppose v has length 1. I can think of f of x plus, say, epsilon v. Do you agree? Okay. Now, if I want to look at the linear approximation in the direction of v, right, then I can just kind of think of this as now a function of the variable epsilon. Do you agree? Meaning that I just plug in a scaled version of vector v. So I evaluate the function along this line where kind of positive epsilon is plus epsilon is this way, and then minus epsilon is this way. Do you agree? So I just kind of decided to I have the function defined on this whole plane, but instead I decided, how about I just think of this function as defined just on this green line, right? And this is now like a this has now become a one-dimensional problem. Do you agree? If I just restrict this function to this line, then I can draw it like usual, where this is kind of in the v direction, and then and I'll get some whatever plot. Do you agree? Okay, now I can do calculus with this, right? Do you agree? So now this will be this was x naught, right? X naught. Now I can do the usual thing. I can do f of x naught, right? Plus I can take the derivative dd epsilon, right, of f of x naught of f at x naught plus epsilon v. Okay. Take this derivative at epsilon equals to 0 and multiply this by epsilon. Overall, yeah. Okay, do people see what I did here? What this represents on this diagram? So, sorry, this is f. So I have some function that takes in points in R2, maps them to the real numbers. Do you agree? Yes. Now, I look at a point, I fix some point x naught, I just chose some point, right? And what I want to do, I want to look at a linear approximation of f at this point. Right now, I don't really know how to do many dimensions. I know how to do only one dimensional derivatives, right? So I say, okay, let's just choose one direction, a random direction that I want to look at, v, right? And suppose v is, say this line, this direction. And now I can look at how f changes if I were to go in this direction. Do you agree? And that would be given by me taking the derivative of f of x naught plus epsilon v with respect to epsilon, right? It's kind of like I'm fixing the vector v, I'm fixing this vector x naught, and by changing epsilon, I get to evaluate the function kind of along this line, up and down. Good question, because I want to look at the linear approximation at this point x naught, right? So I want to look at what the derivative is of this function at this point. And the derivative of this function would be, at f of x naught, would be setting epsilon equals 0. Okay? So I've kind of turned this into, I can think of it as some new g of epsilon, right? For some choice of x naught and v, some g of epsilon. And so I can plot this g of epsilon. I can take this derivative, and so this is like g prime at 0. Right? And so what this is then saying, this is saying that g of epsilon is approximately equal to g at 0 plus g prime at 0 times epsilon. Yes? So this is the same thing as this. Do people see why? Yes? Okay. Let me take a sip now. Okay. But now, let's remember. Okay, so we now got one direction down. There's so many different directions I could choose. Right? I could have gone it this way, that way, that way. I want to somehow be able to capture all of this at once, in one go. How are we going to do this? Well, we're going to look back at the definition. We said the derivative is the best linear approximation at a point. Right? In some sense, so this is R2. How many directions that are kind of independent do I have in R2? 2, yes. And in Rn, I would have n. Okay. Good. So, if I want to have a linear approximation, right, it has to be, so if it's a linear approximation, then my derivative has to be some map, right? because that's we're going by analogy. It has to be some map in one space, and then sends it to a vector in the next space. And I'm going to draw a picture for that in a second. And okay, let's form this diagram, but a little bit more into n. I can draw. I have some. It's no, yes. And okay, I can take some direction v. I can choose some direction v, right? Before this used to be a map of just R. Give me some function that outputs me. If I did the exact same v of epsilon v in the same way, it's just that now this is what this is. This will give me an confused. So, uh, so the x epsilon v, right? F of x is in, so a vector outputs another vector. Denoting the coordinate individually of x, that as of x, whereas this is the second coordinate. This is the you can just define the function because the coordinate x is f of x. Let f second component of let the f. And so this way I have a definition derivative in one variable, even though I'm taking a derivative of a component vector, that's fine. It only depends on a single variable. And you guys this in like physics 151, right? You have a vector and you take dd vector and find each component of the exactly you know position is equal to I have the derivative to the first do you agree with this be the best approximation f of x direction. I'm saying if I was a little bit wrong in the direction, let's take the derivative. How much of my function change, right? Because actually that's true. No matter what the derivative is. Let's be proof. I'm having fun. Okay. Let's remember what the derivative is. A derivative, so d epsilon, f goes to 0, epsilon of minus x. Agree? This is the limit of the component, right? X plus epsilon v dot of and v kind of have to take the limit. Kind of means really. Okay. So we start with n vector, right? So m dimensional vector is now point right? This would be f I applied it to v and I got the vector. Okay? This is how we want this used. I haven't defined it. I don't know what d. So d linear approximation applied to vector v. And so df is 1 over. Alright, so we're about to df is. What we're getting is the information that it's a vector and somehow a vector here around this point. It tells me that okay, if f of x, if I move this direction, my function kind of goes this way. Okay, my vector is. If I go this way, my function will be changing in this direction. Okay, that makes sense. That's if I this linear approximation locally, this would kind of be going in this direction. Okay, like I said, I have directions here, and different, distinct directions. And if I want my derivative to be a best linear approximation, what kind of object should the derivative be? Linear approximation. So the derivative should be a. So the derivative is some kind of linear, right? That takes it to some direction here. Which means that if I was to go in this direction, the kind of keeping, right? So in the case of r, it's really left to right. So there it's like if my function goes, my I move around my space this way, then the function will be equal. But if you imagine like your function doesn't have more directions that you can change, right? You could plot graph where you have something, you have some surface here. That's weird, and you could be like, if I start here and I move this way, the values kind of go up in this direction. So something like that. Okay. Well, no. This is F R. This is a bad example. This is not what I mean. It's very hard to you can't run. So this is an example of where I like it goes up. Okay. This is the right one. Yes. Yeah. N, because it's a function from Rm to Rn. F, the output has x, right? So we can f of x, write f of x as some f1 of x, the x component, f2 of x in the second component, so on and so forth. And there has to be n because the output is n. Okay. X dot would have n. So we figured out how to do a directional derivative. Do you agree? So let's try and formalize this. So um, let f from R. So the derivative at x naught in is this thing, f naught plus epsilon v equal to, okay, this thing. So limit to epsilon goes to 0, f1 epsilon v minus f1 x epsilon dot 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 lim epsilon goes to 0 plus minus n x. You understand this? This is how way are this vector is going to be telling you that why not, which is equal to f of x. Okay? Started at f of x and moved in direction v by epsilon. Out here, oh sorry, m from m to rn. Sorry, thank you. Yeah. So what this means is, if I were to start here and move a little bit in the direction by epsilon here, then map it by f, that would be the same as me starting at y naught and then moving a little bit in the direction dfv, which is some derivative by epsilon. Okay. Do you see how this means that? All the directions together. We said that it has to be a linear approximation. We said that to be linear map, right? Exactly. So, yes, to the vectors and the basis, exactly. So if I want to define this linear map, all I have to do is tell you how it acts on the basis. So if I have n directions, right, all I really need to tell you, like intuitively, is all I should really need to tell you what's the best approximation going this way, what's the best approximation going this way, what's the best approximation going this way, and whatever the other directions are, and that should be enough for me, and I should be able to define my linear map. Yes. So what I can do is I can choose some kind of basis around x naught, right, and then choose some kind of basis around y naught, and write a matrix at the end of the day. Yes. I told you, the derivative is defined to be the best linear approximation at a point. It is defined to be that. Great question. This will be left without proof. Like, if I actually proved all of this, this would be too much. So yes, this is something you do have to prove, and you have to worry about it. But, yeah, you have to worry about it. I won't worry about it. I want you to see the picture of what's happening, and then you will prove all of this in second year. Okay? Or, I mean, you can go ahead and read it yourself and do it. Because at least how I found a lot of these proofs in second year is like, I kind of understand what's happening, but then I look at the proof, and the proof would be like complicated, and like there's a lot of details to it, and I'd get confused in the details and not see the big picture. So this is the big picture that matters, and then the small details you can think about them later, but they're important. I agree with you, but that's not what I'm trying to tell you. Okay. So, but yeah, you should actually, if you have a comment like this, you should make it so that we are keeping track of the things that one would need to worry about. So in that case, so I will choose. I'm going to do a bad thing, and I'm going to use a word which I haven't defined in this reading group. So we should choose an orthonormal basis, but that's okay. So that's kind of like we're going to choose vectors that are perpendicular to each other and are each of length 1. Okay, that everyone understands. And okay, so we will now define. We now define the Jacobian. We will define it through its matrix directly. So the Jacobian, actually no, we won't do that. So okay. So okay. Once again, let f be from Rm to Rn. Okay. Let E1 up to Em be an orthonormal basis. So once again, when I say orthonormal basis, for the people who haven't done the quantum mechanics thing watching the video, that's vectors that are perpendicular to each other and of length 1. And hopefully you know what a vector of length 1 is in Rm. So let it be an orthonormal basis of Rm. Do you agree? And let hi. Okay. And let what's another really good letter that's not E? E twiddle? Or is that confusing? E twiddle with a twiddle on top. Or like a tilde. Okay, fine. E1 up to yeah, sure. E1 up to En be an orthonormal basis of Rn. Okay? And so we define the Jacobian. This is visible right here. Define the Jacobian the following. So, define the Jacobian, we'll call it df. And at the point, so df at the point x naught, to be a map from Rn, from Rm into Rn. Define the Jacobian df from Rm to Rn as follows. We will define how it acts on the basis, right? In the usual way, where df at x naught applied to ei or ej will be d epsilon f of, what should I write here? So this is the best linear approximation applied to ej should give me yes. So I'm just saying that suppose, let me draw the same diagram again. This is Rn, this is Rm. Do you agree? I would have, I'm say at some point here, x naught. Right? And suppose this is two-dimensional, so I'll be drawing it as two-dimensional. Suppose I choose, ei kind of going here, and then some, e1 going here, and some e2 going this way, right? And they're orthogonal, they're 90 degrees between each other, right? And I have the point f of x naught here. Do you agree? And so then all I want to do is, okay, I want to say my Jacobian will be the thing that maps this guy to the best linear approximation in this direction of the function, and this guy to the best linear approximation in this direction of this function. Do you agree? And so, okay, and this will be mapped to some, I don't know, this will be mapped to some d f x naught, I don't know, e1, and this could be mapped somewhere else, I don't know. Right? It's an arbitrary function, it could really do whatever. Okay. Yeah. Okay, now let's, okay, this is all nice, but I want to write down a matrix for things in the end, right? I want to write down a matrix for things in the end. And so let's choose, a particular basis, a particularly nice and convenient basis. The point is that on these things you could be doing like changes to bases and things to work out, which is a good comment. Okay. So let's do an example. Okay. No, let's write down the general thing first and then do this. I should also introduce what a partial derivative is, but that's for later. Okay. Actually, I should do it now. Okay. Okay. So let the EIs above be the standard basis. Standard bases. So meaning let's say E1 is equal to 1, 0, okay, up to 0, and this is m coordinates, and so on and so forth. E2 would be 0, 1, and okay, all of these things. Yes. Okay. Now let's write down the matrix with respect to kind of this E and E total basis of D f x naught. Okay. So I'm going to be on the input, I'm going to be plugging in, so E1, E2 dot dot dot, EM, and on the output, right, the output here is going to be E1 twiddle dot dot dot. Maybe let's do E2 as well. E2 twiddle dot dot dot. EM twiddle. Okay. Remember from what we learned about what matrices are? Oh, right, it's this. It's too much. Okay, I made it worse. That's fine. Remember from what matrices are, is that this column vector is just going to give me df of E1 in this basis, right? So this column vector would just be the coordinates of df applied to E1 in this basis. Agree? Yes? Okay. Now let's briefly remember what f was. So f of x, right, was really just, we decided to choose this notation. f1 of x, f2 of x, right, dot 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 fn of x, right? So all of these kind of these functions of one variable output, right? If I have a function of n variables, I can just, with output in n variables, I can just look at each component separately and then that defines n functions. Yes? Okay. So if I look at E1, E1 is what direction? That's just direction with 1 in the first component, 0 everywhere, right? What kind of derivative does that correspond to? That corresponds to varying which coordinate? The first coordinate. So this best approximation should be like taking the derivative with respect to x1. Okay? So taking a derivative in this direction is as if I was taking the derivative with respect to the coordinate x1. Okay, we'll see why that works in a second. Okay, and this says, okay, I want to look at the first component of that, right? In the output. The first component in the output is f1. Okay? So this has to be the partial derivative of f1 with respect to x1. Okay. If I go next, this has to be the partial derivative of what? F. Think about that again. I want the output to be the output in which coordinate? The second coordinate, so it has to be f2 with respect to x1, right? Because E1 is the thing that says the direction in which I'm changing around here. So E1 kind of says I'm going this way, right? And that's what taking a derivative with respect to x1 means. It means I'm taking a derivative in the E1 direction. Sorry, I'm being unclear here. I'm very sorry. What I mean here, when I say this, f of x is equal as a function of f of x1 dot 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 xn. Wait, I should have defined this, right? So I can rewrite the vector x as some x1 up to xn. Do you agree? And so now, okay, right. I should have defined what a partial derivative is. I'm so sorry. I'm being very. Oh yes, xn. Sorry. Correct, xn. And so a partial derivative. So I guess people can see here, right? Or the Zoom people. Well, there's no one on Zoom. There's just recording. Should I write it here, or do I have space somewhere else? I don't really want to erase anything at all. I can erase this. This is like dated now. It's no longer relevant. We've gone beyond this simple example. Okay. Right, so definition. partial derivative of f from Rn to Rm with respect to x naught. What I'm about to define is really the exact same thing as the directional derivative. It's like exactly the same, but I'm just doing it in coordinates. Is the derivative of yeah, I'm just doing the exact so it's denoted like this with respect to x1 at p. So at p is equal to just the I kind of fix all of my entries and take a derivative with respect to xi. Sorry, x. I'm saying let's look at this point. Fix what the value of all the other coordinates are except for xi, and so think of it as think of it as now a function of just one variable, which is xi, and take a derivative in that direction. You may recognize that then this is kind of the exact same thing as I was saying with this. You may see that what I wrote above is the exact same thing. If instead of writing stuff in coordinates, I wrote stuff in terms of like vectors. Do you see how this is the same thing as this? Please say no if you don't. You look still confused. Do you see how this is kind of the same thing as this? Now, I started at point P, and I say I can only vary the eith coordinate. And so then the derivative of f with respect to, with respect to, let's say, xi. So this should be the same as this. If I only vary the ith coordinate and keep the rest of the coordinates fixed. Yes. Now, how is this different from like this? How is this partial symbol? How is a partial derivative different from a total derivative? Right? Let's do a few examples quickly. So if I had, suppose I had a function f of xy, and it just gave me x times y, right? Okay. If I did a partial derivative, so partial f partial x, I'm assuming that y is some number that is fixed, and I take a derivative with respect to x. So if y is just some constant, what's the derivative of this with respect to x? Y. Yes? Because then this is just x times y is some constant derivative of a linear function, is just y. Yes? Okay. However, if I took a full derivative of f, right, this would be d dx of xy. This would be y plus what else? Plus x times d dx of y, because you don't know y could depend on x. What if y was a function of x? So a full derivative kind of assumes that everything could be a function of the thing that you're differentiating with respect with, versus partial derivative says, okay, let's just do things symbolically, right? If the symbol is not x, then it's constant and doesn't change. Okay? So do you see heuristically the difference? Just a little confused. Do you see the difference between a partial derivative and okay? Do you see why we, in our case, we want to use a partial derivative, right? Because we want to kind of isolate a single direction and only be looking at the linear approximation in one single direction, right? And only assume that we can kind of fix everything else and say that we can only move in this way and not any other way. Okay? That makes sense? Okay. So, and that is why here I have to be taking a derivative with respect to x1 of the first component, or of the first component of the second component, so on and so forth. Partial f n di x1. Okay, so what I wrote down here, that is in fact just that guy if I wrote down each single component. Agree? What I wrote down here is the same thing as writing, subbing in I to be 1 and writing this out component wise. Sorry, this would be up to xn. No, yeah, xn. Yeah, that's right. That's right. FN, sorry. So do you see how this? Let me show it to the video. This is in fact the same as that. So this column vector is the same thing as this vector with I equals 1. Right? Because this is, I took the derivative of the function in the direction kind of xi, ei. Yes? And so that's what this column vector is. So that's what it is. Right? I'm just taking a linear map and I'm writing it down in some basis. I'm just telling you, what, where E1 gets mapped to, E1 gets mapped to this. Because that's what we said it should be mapped to. Okay. So then E2, okay, E2 is going to be what? In the x1 direction, it's going to be partial. In the x1 direction, it's going to be partial f what? No, think about it. So this is it. So the input means that I'm changing my variable in direction x2. And this is the output, like how much I'm moving in the direction u1 in the target space. So this is saying that if I was to move this way here, how would that correspond to like moving a little bit in this direction? How much, if I moved in this way, how much would I move in the direction like e1? So this would be partial f, which one? F1, partial x. Yes? X2, yes. Right? Because the partial x2 is saying I'm taking a derivative in the direction x2. So I'm moving in the direction x2 here, and then I'm looking at all the basis vectors here and just writing down that the vector that I get from moving in this direction, what does it look like here? Okay, and okay, I get partial f2, partial x2, partial fn by x2, so on and so forth. And so if I did in the center ei, sorry, ej, this would be partial f I partial xj. Uh, yes. Yes, so this would be the gradient. But I don't quite like that way of thinking about it, because the gradient isn't the fundamental thing here. Like the gradient is an example of a Jacobian, right? It's just for a function f being mapped from Rn into R. Okay. So let's look at now that I'm thinking about it, I wasn't planning on doing an example, but maybe we'll do an example. How much time do we have? Perfect. We still have. You guys you see, you told me that you don't have a midterm tomorrow. So if you don't have a midterm tomorrow, then you can stay a little bit longer. Huh? Tomorrow is Saturday? Yeah. So you don't have a midterm tomorrow. Yeah. That makes sense. Makes sense to me. Yeah, exactly. You have until physics closes at 9. Okay. So this makes sense, right? Okay. let's then try. I can erase this, yes? No, a lot of the stuff that I'm omitting here is like, okay, the Jacobian, like any derivative, has to exist, right? It doesn't always exist, right? You need the function to be differentiable in some sense, right? So, but for the function to be differentiable in some sense, you can just think of, oh, maybe all I need is my f1 and fn to just be differential at every point in the, like, all the xi's, and that's enough. Okay, it is enough. So that's it. Or I think it is enough. Maybe I'm wrong. I need to think about that. But yes, like, I'm kind of skipping over all the facts of, like, when does this exist? When, when is it well defined, so on and so forth. There's conditions that you can write down, which, if it's in physics, it's invertible, injective, I don't know, whatever. Whatever you want it to be, it's very nice. And definitely differentiable and smooth. And, well, except for when in quantum mechanics we learn about things that aren't smooth. When you observe something. That's okay. That's a different reading group. So let's look at this example. Let's look at two examples. So we'll have a function x, y that takes in x and y, and okay, let's do this one first, right? Okay. So df, well, choose the standard basis, right? As usual, note this is a function from R2 to R. Okay. So df at some point x naught. Let's compute this function at, say, at the point so at the point 1. Also, all of these partial derivatives, all of these are evaluated at the point b. All of these are evaluated at the point b. Okay. Well, actually, yeah. So let's section. Let's write something general. So let's write this. No, let's write this df at point xy. Maybe this is confusing. At point x naught y. Okay. So this is the derivative is some linear approximation of some matrix in our case. We're going to compute what this matrix looks like at point x naught y naught. Right? Okay. So what are the dimensions of this matrix? How many rows and how many columns? So don't say it out loud. So raise for how many rows are there fingers? Raise it by fingers so that other people have a chance to think about it. How many rows are there in this matrix? Rows. Rows. Yes, so it's 1. Rows. Because row is what? Row is the output. You have only one dimension for output. Right? Because this is function from R2 to R. It's just x, y. Yes. So there's only one row. How many columns are there? 2. Okay. So I'll draw something like this. There's going to be 2 numbers. So what are these numbers going to be? So here, I'm going to, in the first component, I'm going to differentiate my function with respect to x. And then the second one, y. Okay. So what's the derivative of x with respect to y at the point x naught y naught? So let's write this out. I want to take x, right, with respect to x, and evaluate at the point x naught y naught. Yes? And then I want to take the derivative of f with respect to y, and also evaluate at the point x naught y naught. Do you agree? Okay. So what's the derivative of f, partial derivative of f with respect to x? That is y, and we want to evaluate y at x naught y naught. Okay, and the derivative of y with respect to x is, the derivative of f with respect to y is x, and I want to evaluate that at x naught y naught. Okay. What is y evaluated at x naught y naught? Y naught? And x evaluated at x naught y naught? Okay, this is my matrix. Right? What? So let's see. What is this telling me? So this is E1, E2. Okay. This is telling me that okay, I have some function x y, right? It takes two numbers in, outputs one number. Suppose I was at this point, and I have a vector E1 is this way, right? Because that's the x. E2 is this way, and this is the point x naught y naught. Okay. And then I have some point x naught times y naught, right? Which is just f of x naught, right? Okay. What this is saying is, suppose I moved in the E1 direction, right? Suppose I moved in the x direction. Right? If I moved in the x direction and didn't change y, then this would quite literally be a linear function of x for some fixed y naught, right? So if I was to go this direction, the derivative would just be a linear function with y naught fixed, right? And so the derivative would just be y naught because that's the slope, right? Okay, and if I went up, right, then in this function, the x, if I go directly up, then the x is fixed, right? And only the y is changing. So now, of course, you will see all sorts of notations. Sometimes instead of df, people literally write just this to mean df, to mean this whole matrix. Sometimes people write this, right? Without just, they aren't specifying which xi they're differentiating with respect to. So that means that, they're just differentiating with respect to all of them, so it has to be the matrix. Sometimes people write this. Sometimes I think I've maybe seen like something like this be written for when this actually means, for when it's like not a function from Rn to R, it's actually a function from Rn to Rn, and someone wrote this, but okay, that's not so. That's like, I haven't really seen that. Maybe once. Okay. Now, the gradient actually is really special. In what sense? Because the gradient, so we said that the Jacobian is a map, right? It tells me how a vector kind of here locally would get mapped into a vector somewhere here at this other point locally, right? But in this case, the gradient, even though it's a linear map, is actually itself a two-dimensional vector. So if you really wanted to, you could plot this back in R2, and it would mean something. But I will not touch about that point too much right now because you already look confused. And so that would be on your suggested exercises. As like a bonus suggested exercise. How many times can I add the word bonus in front of the other word bonus to have like multiple layers of being bonus? Yes. It's all bonus anyways. It's like some things are more bonus than others, but when you come here, all of it is required. It's like, it's optional to do in your free time, but once you're here, it has to be done. Okay. Okay. So we'll now denote this Jacobian thing as a df. And so let's write down a final kind of, let's write down one more thing about df to kind of understand what it really does as a linear approximation. So as a linear approximation, what it's telling me is f of x naught plus v, where v is just some small vector, should be approximately be equal to f of x naught plus df evaluated to x naught, all of it applied to v. Right? And this makes sense. Yes, this is a linear approximation. If I go in direction v, then my function should be approximately where I started off, plus, in which direction I traveled and by how much, and, the matrix that applies to it, right? When we just had a usual derivative, we didn't really have this problem because you only had like right or left, so just plus or minus, right? That was really only one direction. But now you could be going up or left, but those two could like mix in some sense. So it's more complicated than that. Okay. Okay. So now, what can linear maps be? We want to study this a little bit. What can linear maps be? They can be. They can be what? Well, no. That's sure. Yeah, actually, yeah. Maybe we'll talk about that first. But in general, they can be two things. Well, they can be injective and surjective. Okay, that might be useful things to think about. But actually, let's first talk about. Raise your hand if you looked at the tensor question. Okay, let's finally see why the tensor question mattered. Why this all was so important. Um, Maybe I should do one more computation where it's like a two-dimensional function, but actually I'll just give you a bunch of exercises to compute Jacobians. Actually, one of the Jacobians you've already seen in 240. I asked you to compute the determinant of a certain Jacobian that was very relevant to physics. And of course now, you'll have the privilege to compute the Jacobian first and then compute its determinant. But so, why do we want to compute the determinant of Jacobian? This is going to be a really great question. Can I erase this example? This is important. Write this down. Write this down and write down the definition. So, like, this is the whole point of what we just did. Everything we just did was given a function and a point, define a linear approximation, so some linear map that takes f of x naught, and then you add some v times the x naught, where v is kind of the displacement away from x naught. And this is kind of good in some sense. This is really, you can really take this to be the definition of the Jacobian instead of that. Okay. All right. I will now erase this. And now we're going to restrict ourselves to the case of suppose f is a function from Rn into Rn. And suppose this function is invertible. So it is some kind of coordinate transformation. So invertible and differentiable. So in some senses, like Jacobian exists and is nice. Actually, wait, this is true. All the coordinates are like sufficiently differentiable. That's not enough for the Jacobian to be like nicely well defined. Right. There's like some counterexample which I'm forgetting and it's escaping me. So remember, so if you want to have a Jacobian, always, I said like, oh, it's enough to have all of the components to be differentiable by all the xi's sufficiently many times. But I'm not sure if that's entirely correct. So, but I need to like double check these things. Okay. That's not the point. Okay, so suppose Rn is invertible and differentiable in like our way that this Jacobian thing exists and does something like this. So in like this very loose intuitive sense. So what was the tensor question about? Why did we need alternating tensors? Why did we need alternating tensors? Volume. Exactly. So it's a central question to physics is to compute the volume of something. Right? Or compute the area under something like that. So sometimes it is not convenient to compute the volume of something in one coordinate. But it's more convenient to compute the volume of something in a different set of coordinates. So how do we do this? And okay, then after that you can go. Because I think you're, oh, okay. It looked like you were packing up, sorry. That's fine. So suppose I have a set A in Rn. Okay. And then I have a set f of A also in also in Rn, right? So question, how is volume, of A related to volume of f of A, right? Do you agree? It's some set, some nice set. Nice set so that it has a volume. Not all sets have volume necessarily. So yes, yeah, go ahead. No, it's some function, any function you want. Maybe we should have started with a case where f is linear, but we won't. We'll just do the hard thing straight away. So, okay, let's look at the volume of f of A. So, it's related to determinants. That's the point that we're about to get to. So, don't spoil the answer. I didn't ask you to tell me the answer. I want just okay. So the volume of the function f of A can be defined as the integral of just one, the number one, over this set. Do you agree? Now, okay, maybe we don't really know exactly what a multidimensional integral is and how that's well defined and whatnot, but you can imagine that in some sense, I can do some integral over this set. Do you agree? Straightforward. Gee, this is something maybe I should have talked about Houdini's theorem first, but that's okay. We'll talk about that later. That's not the point. I'm doing everything in like reverse order right now. It's exciting. Okay, so the question is, how does this relate to some integral over A? Right? We're saying that we want to find the volume of f of A, but if we use the A, this would have nicer coordinates if we thought of it as A, and so we want to kind of relate this. Okay, so once again, I'm going to draw the same drawing I've drawn 100 times today. Let's try it yet again. No, but this is going to be a little different this time. Now, okay, this is A, and then this gets deformed into something weird, f of A. Do you agree? And then this is f. Now let's look at a point. Do you agree? Let's point some, I don't know, some x node. And what can I do? At this point, I can draw some little bit of volume. So some parallel plate. Some parallel plate, but a very small volume. So let's see if my artistic skills are up to the task. No, they're not. Right, because this has to be dashed. Like this. So something in the back like this. Like this, like this. Like this, like this. Like this. Okay, I have some little volume around this. Okay? So, and let's say this is like, E1, E2. No, this is E3, this is E2, whatever. Some basis, whatever. Do you agree? Okay. And now I want to figure out, so this is how this little volume looks here. In these coordinates, it's like flat. I want to see how does this function f change the shape of this box, right? How does this box, once I map it, change this box, right? At this point. What thing tells us how this box changes? The Jacobian. Right? Because this box is made of vectors E1, E2, E3, so on and so forth. The Jacobian is going to tell me how these vectors will transform once I kind of push them into here. Do you agree? Okay, I'll make this a little bigger so it's easier for me to draw. Okay, and so suppose this is f of x naught. You know, these three vectors could have been mapped by after something really weird, like that, and say like that. So it's no longer like a straight box. It's somehow like curved. Well, not curved, but like slanted. Like think of an Amazon box, and then you like tilt it and like squish it. Yeah, sorry, not curved, but like slanted. It's a parallelepiped, but like not a straight one. Okay, I'm drawing this like horribly, but okay, it's some slanted box, right? And now the vectors are what? So here it was E1, E2, E3. Now the vectors are D, F, E1. So df at x naught E1, df at x naught E2. Oh no, this one. The one up is E3. This is df x naught at E2. Okay, do you see? And now we want to compute the volume of this box, right? But the volume of the previous box was what? 1, exactly. So, well, what was, remember, the determinant, so recall from the question, recall depth of a matrix, some matrix M of T, this was the volume of parallelepiped, okay, some other letters which I don't remember, parallelepiped formed by column vectors. Okay? So if you had some parallelepiped and you made it out of some vectors, right? And then you put them, sorry. If you have some parallelepiped made out of some vectors, so you have this vector, this vector, this vector, that defines some parallelepiped for you, right? If you took those vectors and you wrote them as like the first column vector of a matrix, second column vector of a matrix, third column vector of a matrix, if you computed the determinant of that, that would give you the volume of that parallelepiped. And that is what the suggested exercise had you learn on your own. Yes? Why that has to be the case. There's no other thing that could do it other than the determinant. If you didn't do that exercise, that's no problem. But that's what the determinant does. Okay, now I have a parallelepiped formed by df applied to f1, df applied to e2, df applied to e3. Right? So the volume of that has to be the determinant of what matrix? It has to be the determinant of the Jacobian, right? Because the column vectors in the Jacobian, they tell you precisely where E1 gets mapped to, how E1 gets deformed, how the direction E1 gets deformed, how the direction E2 gets deformed, and how the direction E3 gets deformed. So the columns of the Jacobian already explicitly tell you where this kind of side gets mapped, where this side gets mapped, and so on and so forth. It immediately tells you how your box got deformed. It actually gives you the column vectors, the sides of the deformed box by definition. Do you agree? So now what we could do is, okay, I want to sum up all of these boxes, many tiny boxes at every single point, right? So I want to do an integral over this area and add up all these boxes. But now I know that this box corresponds to this box here. So instead of doing an integral over f of a, I can do an integral of a, but instead of adding up the volumes of these boxes, I'd be adding up the volumes of these boxes. Yes? So the integral from this, the big takeaway, can I erase this gradient stuff? So the big takeaway of all of this is that the volume, yeah, of FA, which is, we said it's some integral, whatever this means, FA of 1 has to be equal to the integral over A, where I'm taking the integral of the absolute value of the determinant of the Jacobian of f evaluated at x. Oh, sorry, f, yes, evaluated at x. So I'm taking an integral over x. So x is now in A. Right? I'm taking a point x in A, looking at what this straight thing, how it would look curved here, compute the volume of this curved thing, kind of add up over all the boxes here. But remember that f was invertible, so I can kind of look at every point here, look what the box kind of looks like at this point here, and then take the integral. Oh, sorry, this has to be absolute value. Yes, I take the absolute value because the determinant can be negative, whatever. Yeah. Here we're assuming that like the area of the set is positive. Yeah, yes, but that's let's sure, but let's not talk about that. Do I need absolute value signs around the number 1? If I take an integral of a positive thing, I'll always have something positive. It's an integral of a constant function 1. Yeah. It's kind of like, yeah. There's a lot more I could say about this, but in general, I'll write down the thing. In general, if I'm taking an integral of a function g of x over f of a, that has to be equal to the integral of the function f, of the function g of f. Well, let's do g of y. G of f of x times the determinant of df x over a. Okay, so this is the change of variables theorem. I'm not proving it because that's like a 5-page proof, which was preceded by like another, many pages of proofs. But intuitively, I want you guys to really see intuitively why this is like this has to be the only thing that works from this diagram, right? Because if I'm integrating some function, right, around here, right, this integral is saying like, okay, I integrated this point and choose kind of straight coordinates here, straight coordinates, right? That's what this is doing. But if I wanted to integrate over this instead and still get the volume here, I need to see how does a straight box, how does it get curved by f, and compute the volume that way. Okay. Does this kind of make sense? The picture. Do you see how from this picture you have this side? Yes. When you're still confused, that's okay. That's fine. This you didn't do the exercise. Okay. The only part of the exercise is that just assume that the volume of this box is going to be the determinant of df. That's it. That's all that exercise is. And I'm saying that if you want to compute the volume of this guy, right, I can just take the volume of this guy and just scale it at every point, right? And if I know this box gets into this box, right, and this point will contribute determinant of df of volume, right? So if I want to look at the volume of f of a, that's like adding summing ones around the volume of f of a. That would be the same as summing determinant of df at every point in A, right? If this region gets mapped into this region, then the volume of this should be, I'm kind of taking and curving the volume locally at every point and adding it up at every bit. So, you kind of cut this up into you take this, cut it up into little cubes, right? And then see how each one of those cubes gets deformed, and then add that up, right? So that's what I'm doing. I'm cutting these cubes up, seeing how they're deformed, and adding them up in A, rather than, so this is like adding straight cubes up in F of A, but this is starting at A, deforming the cubes as to how they would look here, and then adding them up. You were going to ask them. You swap, you change the orientation? Yes. So don't change the orientation. This is, okay, you're right. This is like assuming that there's a fixed choice of orientation. And then you always integrate from small x to larger x. And always integrate from smaller number to larger number. That kind of thing. So yes, you're right. Both of you are right. Orientation matters. But let's not think about it too hard right now. I just want to understand the idea of you can take a box and squish it, and that will have a volume. Okay. Yes. This is that idea of you take a box here, you squish it, it changes its volume. The change in volume is given by the determinant d of f because you did that in an exercise. And so instead of adding up straight boxes here, I can add up over the region here, and I can just add up the volumes of the curved boxes, not the slanted boxes. And that's what gives me the volume. Okay? So this is the change of variables there. Now, how much time do we have? We have plenty of time. We have a whole 12 minutes. And I'll define what an inner product is in the last 5 seconds. Well, actually, I don't know if I should do it now or if I should just shouldn't do it at all, because I don't know if this proof is useful that much. Okay, I'll just state a result. And I will not prove it, but I will maybe leave it as an exercise or something. I don't know. Or you can come and ask me in office hours. This is a proof in Mongoose. So this is the following thing. I didn't write that. Oh, right. This is a certain someone's office hour, I think. Something like that. I don't know. So let's do. So this is the inverse function here. This is a fairly important result to prove in second year. I was going to prove a little subpart of the result, but yes. Yeah. But okay. So let f be a function from Rn into R. So sorry, let's kind of look at the motivation of why we want to prove this theorem. Right now, I just told you if I have some invertible function which is differentiable and nice in some way, then we have this thing about integrals and determinants and how to relate to integrals. Okay. However, the problem is, well, when exactly is a function invertible? How do we know? Right? That's not a question. That's rhetorical. And in fact, the Jacobian kind of helps you, gives you some conditions on when the function should or should not be invertible. So let's look at the following. What does the Jacobian do? It kind of tells you how do my coordinates here get warped when they get mapped to the new place. Right? That's what the Jacobian tells you. Right? How does going in this direction get? What direction does that get? What does it mean if I go in this direction? and then I get mapped, which direction would that correspond to going into? Right? Kind of tells you how does this get worked locally. So if the Jacobian is, I said that the Jacobian is a matrix, and a matrix can be which two? It's a linear map, so it can be which two things? Injective and surjective, right? So particularly it can be bijective, so invertible. So if you think about it, if the Jacobian is invertible, what does that mean? Well, no, that's not relevant. The determinant, we only care about the determinant for volumes. Forget about the determinant for any other reason. Yeah. No, that's right. But the determinant being zero is like a useful computational tool. It's not interesting. Well, it's interesting, but not interesting in this context. So if the Jacobian is invertible, right? This means that every direction in this, so every direction in this space, sorry, every direction in here gets mapped to some direction in here, right? So going somewhere here means that I'll be going somewhere, somewhere in here. Right? If it wasn't invertible, that means that going some direction here would be equivalent to staying in the same spot, right? So actually, that means that if I go in some direction, my function won't change at all, right? Intuitively, because if it wasn't invertible, that means there's something in the null space. If there's something in the null space, that means going that direction, my linear approximation says the function is not really changing. Okay, that's something we'd also need to prove, but doesn't matter. The point is, yeah. So, but this means that if the Jacobian, my camera froze for some reason. This means that if the Jacobian, let me just redo this. Let me delete this video capture and add new video capture. We're almost done. Because I decided to just not prove this fact. Oh, my camera just died, question mark? That's exciting. Yeah, this camera is just not working. That's maybe not good. I'll use my own video camera. Okay. Okay, great. So if every direction here gets mapped to some direction in here, right? This means that if I go in any direction, that means I'll be moving away from where I started off, right? So in some sense, locally, if I move away from where I'm at, then I'll keep moving away from the point. That means the function kind of has to be invertible because there isn't any direction in which I'm staying the same, like sufficiently close. So the inverse function theorem says that, okay, if I have some function from Rn to itself, and the Jacobian at some point x naught is invertible, that implies there exists a ball of some radius epsilon around f of x naught, and exists a ball radius delta around x naught, such that a ball. No, it's not necessarily a ball. That's the problem. It's like two open sets. So, well, yeah. So let's say this way. This means that exists a ball of radius delta around x naught, which is really just all y such that the distance between x and y is less than delta. Okay. Such that f inverse restricted to the image of this ball is invertible. So is in fact a function. So is the inverse of f restricted to the ball, I guess. It's not. And is differentiable. So if f is invertible and okay, df is invertible and okay, it exists, is differentiable. And what do we guys think the derivative of this inverse function will be? So if this is the derivative of f, which is some linear map, what should be the derivative of f inverse? It should be the, don't think about chain rule, think about the words. If this is the derivative of f, what should the derivative be of f inverse? Recall this is a linear transformation. It should be the inverse of the Jacobian. Yes. So it is differentiable with Jacobian. You just have to make sure you plug it in at the right points. It is differentiable with Jacobian df at f inverse y. Wait, sorry. Yes. Inverse. Did I have too many brackets? No, that's right. So why did I write f inverse y? Right, because I have to make sure that I'm evaluating the Jacobian at the right point, because f inverse goes from like y to x, right? I have to make sure that I'm looking at the Jacobian at the point that maps to y, and then taking the inverse of it. I think that looks right. So the Jacobian, sorry, the Jacobian of f inverse at y is equal to this. Right. Where f inverse of y is like the point at x. Okay. This is central theorem. But you can see why this is true, right? Because this means that in some sense, if I'm at a point and the Jacobian is invertible, that means if I go in this direction, that still corresponds to moving away from the point. And if in every direction I'm moving away from the point, that means somehow the function has to be it can't be constant, like sufficiently close to where I'm here. That's the point, right? If going in any direction means I'm going away from the point, that means close to this point, it can't be that the function is constant. So it means close to the, I have some inverse locally, close to the constant. And I mean, you even have that for, you very much have this for single variable calculus. You know this really well from single variable calculus, right? Suppose, so if I have a function from one dimension to one dimension, what does the Jacobian look like for that? It's just a single number. It's just the usual derivative, right? So what we've defined as the Jacobian is in fact in every way a generalization of our usual derivative, because it even coincides with what a derivative is, right? So if the Jacobian is non-singular, all that means is that the function has to be, if the Jacobian of a function, so if suppose my function was from R to R, and it had non-singular Jacobian, what does that mean about the derivative? Sorry, has an invertible Jacobian. What does that mean about the derivative? The derivative just has to be non-zero. So okay, suppose I have something here. And around this point, right, I have a derivative that's non-zero. Do you agree? Yes? It's positive in this case. Okay, but if you look at a small neighborhood around here, right? Since the derivative is positive, there is very much an inverse, to some small ball here that is well defined. Like I can go back here and then go down and have an inverse. If you had, even a sinusoid, right? Here the derivative is positive. Locally, I could really define an inverse around here properly. Okay, but here the derivative is 0. Right? So here I can't necessarily define an inverse properly because two values like this value here and this value here would get mapped to the same thing. So the function around the small neighborhood here wouldn't be invertible, right? But that's not always the case because I could have something that's like this. Okay, and then here I suppose it's like not flat here, but like still slightly increasing, like x cubed. Right? Then here the Jacobian is singular, but I still do have an inverse. Right? So that's the problem. So, well, not a problem, but the inverse function theorem only tells you when they're it's a like it's sufficient. This is sufficient to have an inverse, but it's not required to have an inverse. But also in this case, your inverse might not be differentiable or something. But okay, that's a separate question. Okay. So I was going to prove this idea. I was going to initially take this idea of like, oh, if you're moving, if you go in any direction that's like corresponds to moving away, that means your function has to be at least bijective in some small ball. I was going to prove that to you, but I won't. It's that part of the proof is not very difficult. It's the other parts of the proof showing that okay, this is in fact the derivative and it's it exists and all of this works out nicely. That's kind of the hard part, and but I don't want to because we ran out of time. Okay, right. Inner products. Very brief. Very brief. We will define inner products. So for the people who've been to quantum mechanics, the quantum mechanics meeting is good. We will quickly define what an inner product is. Oh, right. That's not good, but why did that stop working? Can I erase this? Okay. So we defined an inner product, so definition. Let V be a vector space. I'm going to just give the definitions and not talk about too much today. Let V be a vector space. Then, so an inner product is a function. So this is over R or C. This is a vector space over R or C. It's a function from V cross V into C with the following three conditions. So V inner product V is greater than or equal to 0 for all V. 2. V inner product V is equal to 0 if and only if V is 0. So 3. Linear in first entry. So V plus lambda U W is equal to inner product V with W plus lambda inner product U with W. So for all V U W lambda. And 4, right, you can't really see what I'm writing on the camera. And 4 is that UV is equal to the complex conjugate of VU for all vectors. vectors, that's fine. If so, in the quantum mechanics course, this matters in the because things can be complex. In classical mechanics, we'll only consider vector spaces over the reals, right? Oh, whoops. Oh, that's something else. Okay. We'll only consider vector spaces over the reals, and so this really becomes uv is equal to v inner product u. So that's a condition. That's a condition. And so definition, and then we're done. So a vector space with an inner product is called an inner product space. So we say let V be an inner product space. U is said to be orthogonal to V if inner product of U and V is equal to 0. Okay. And you have an example of an inner product is the dot product. You know what that is. And you in fact know that if the dot product between two vectors is 0, then they have to be orthogonal. Well, perpendicular. Okay, and that's just a definition, kind of formalizing that. Okay, that's it. So I'll try and give you some questions, suggested exercises.